All right, what's up, everybody? So today we're going to be speaking about spring mass systems. Okay, so spring mass system is actually a very powerful tool for us to be able to analyze a system and understanding a lot more without the complexity of it. So, especially vibrating systems. So, spring mass systems. Getting a lot better with the pad. So spring mass damper systems. So we have mainly, the ones that we're going to be speaking about a lot is a mass, right? We're going to be speaking about spring. We're going to be speaking about some damper, and sometimes we could be speaking about some rotational mass. Okay, so the beauty is you can actually treat those guys like resistance in a circuit, right? So if you have, let's say, K1 and K2, you can actually say the equivalent of those guys is equal to K1 plus K2, so K equal. Okay, these guys you treat like resistances in parallel. So if you have, C1 and C2, your C equivalent of that, basically it's 1 over C equivalent is equal to 1 over C1 plus 1 over C2. Okay, so now I'm going to show you here the idea, but you can basically model almost anything that vibrates in this means, right? Because it almost always has a mass, it almost always has some stiffness somewhere, almost has some viscous friction or viscous dampening somewhere, and then based on what it is, you could have rotational mass, like vibrators, not the ones you use to excite a system, like shakers. That's that, right? So any type of a vibrator system, usually they have some rotational mass going around, trying to output that energy somewhere. All right. Well, let's go into some examples. Well, let's say I have a car, and this is maybe the most widely known example out there, right? So I have a car, and I have my wheels here, and I have this is, let's say, my frame connected with the spring, the suspension in the car, and then it's connected to the wheel. And then while you're going uphill or something like that, and there is a stone here. So you can actually come and say, okay, you know what, I can model that system by saying I have my mass here, right? So mass, I'm going to say is 0.1. So mass 0.1, right? And then I have some stiffness, and I also have some damping. I mean, that suspension system, I want to dampen it. Otherwise, it would be, the vibration will go and it would just go forever. So there's some kind of dampening, some friction. Maybe I'm going to hold thing from moving, or put something that actively absorb it. You might have seen a lot, the springs with some kind of hydraulic in the middle. That's basically there's basically some viscous dampening in the middle, and then some stiffness outside. And then I'm going to have my M2, which is over here. So MP2, and that's basically how I have it. I mean, you can add another spring and mass for the tires, right? You can say, oh, you know what, my tires are actually made of some elastic material that I would like to model, for stiffness. But for the most part, I think, in order not to complicate things, you can just do this, and you'll be like, okay, you know what, what's up here? So here's my reference. So how do things react when I have some force acting here, right? So some FFT or some initial displacement maybe. Again, it's so fluid in terms of how you define it. It's really up to the situation you are trying to model. Let's look at a different example. So let's say you have one of those like in construction sites, right? One of those things that carry a weight here. You can model that as well. I mean, if you were to stop here, maybe you're getting too much vibrations going on because of that pendulum. So maybe you can model this as, oh, you know what? I have a mass, right? And then I have some spring happening here, right? Maybe I have some structure at the bottom that I have for dampening, right? And then I have some mass again, right? And so in this case with your reference, right? I mean, you have a reference in this case, right? Because you're assuming that this here is a reference. So you have some spring, some damper, you have some mass, right? And then possibly another spring and another mass, right? So maybe you want to understand how do things, transmit inside. So again, it's really up to what are you trying to do. A pendulum, right? That's why I didn't really want to complicate it here, but you have a pendulum in the end, and a way to model a pendulum, right, is you have some reference, right, and then you have some spring, which is this here, right, the material that this is made of. Some dampening is just depending on whatever torque you put out there for viscous friction, actual friction, and then your mass hanging at the very end, right? So many examples. Another example I'll show you, you're probably familiar with as well, is let's say you have let's say you live in Europe or something, and you have a flat, right? And this is your balcony, and you are standing here, or somebody's standing, or you're designing a balcony, and jumping, literally, just jumping. So you want to understand, or maybe you're just standing there, and there is some vibration from the wind on your building that's getting to you. You actually feel some vibrations on the balcony. And again, it's modeled the same exact way. It's modeled the same exact way. So you're going to have your mass, right? And then your stiffness over here, and then whatever friction you put in, whatever dampening you put in the system. Whether it's, some structure of viscous damping or whatever. There's so many different ways of damping. So there are so many, anything you can model as spring mass systems. It will help you clarify, it will help you oversimplify the problem so you can solve it better, right? So 4 things I'm gonna say for steps to how to do this. Number 1, understand the masses in your system. When I say this, I mean the significant ones, because obviously everything has a mass, but you just need to know when is it significant. My spelling is horrible. Let's see. Okay, significant ones. And then understand where the springs are. This is important because using these two only, we'll talk about it later here, you will be able to find the natural frequencies. And this is really the most important thing. I mean, dampening, yes, affects natural frequency a little bit, but not by much. Which, again, we'll talk about that a little bit later here. But the natural frequency is mainly affected by the masses or the springs in your system, depending on how your system is set up. But it's mainly the springs. That's why, again, we'll talk about this later, but let's just say that those are your most important thing to understanding the natural frequencies and such. If you want to understand the modes and the modes of your system and all this good stuff, again, we'll talk about this later, but you need to also understand where is your damping in your system and what type of damping is it, right? Is it viscous? Is it Coulomb? Okay. And then last but not least, understand the structure, like how they're put together, and how are you gonna model it, and what exactly are you looking for. So where are they vibrating, how, and such. Because modeling a real system, I can tell you, I've been running a MATLAB just for fun for a simple beam. So I'm just modeling a driveline, nothing too complicated about it, just one driveline. I haven't added anything to it, and it has been taking days. My MATLAB is not done yet. And again, MATLAB is not the optimized tool for it, but still, you need to understand your system, and you need to understand what's trivial and what's not trivial. So maybe I can take my model and I say, okay, I don't care for 3D. I can do 2D estimations for now, or I can maybe the plane is all I need. Maybe I should model them differently, and that's what basically it is. Anyway, thank you. I hope that was good. If you have any questions, let me know. And I think starting off, I think we're set up good here so that we discussed a little bit of the backbone, so we can start digging into the deep stuff. So I'll see you guys next video.